So another example here. Let's consider a long line of charge and another long line of charge that's perpendicular to it. Now, let's say that there's a tiny little gap here, so these two charges don't bleed over into each other, so they'll call that lambda 1 and then lambda 2. Okay, so let's say that lambda 1 is minus 29.1 microcoulombs per meter. Let's say that lambda 2 is 17.7 microcoulombs per meter. And I've got a spot right here. Okay, and so I've got a spot right there at some x and y. And so let's say that the x position is 7.75 centimeters and the y position is a minus 6.5 centimeters, putting our origin at the intersection of the two. So I want to know at that point, what is the electric field? Okay, so I want to know what is the electric field there. And so we look at it and say, well, due to lambda 1, so lambda 1 is a negative 29.1 microcoulombs per meter. So that means that E1 points towards it. Okay. So the electric field due to a line of charge, is, now there's several ways of writing this. We had written it as 2 lambda k, or 2 k sub e lambda over r. That's the same as the way the book writes it is lambda over 2 pi epsilon naught r. Either way works. Either way is really the same thing because we know that k sub e is 1 over 4 pi epsilon naught. So both are legitimate ways of writing it. Okay, so we know everything we need to know there. So that tells us that E1, the R in this case, so the R is going to be that distance right there. So R is going to be the 7.75 centimeters. So I plug that in, then this is going to be 29.1 times 10 to the minus 6 coulombs per meter divided by 2 pi times 8.85 times 10 to the minus 12 of the coulomb squared per Newton meter squared, okay, times the R, which was 0.0775 meters. So E1 vector is going to be minus 6750 Newton per Coulomb I, because we know it's got to be in the negative direction because it has to go towards the negative charged wire. We have the other wire though, so we also have lambda 2, and we have a point here, and lambda 2 is going to be 17.7 microcoulombs per meter, and so we know that the electric field has to go away from that wire. And so away from the wire, since below the wire, that's going to be in the minus j direction. And so E2 is going to be equal to lambda 2 over 2 pi epsilon naught r, R2. Now R2 is going to be that y right here. So the y dimension was 6.5 centimeters. So this comes out to be 17.7 microcoulombs per meter divided by 2 pi 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. And the R2 is 0.065 meters. And so the E2 vector is going to be minus 4,900 newtons per coulomb J. So the total vector is going to be the E1 plus E2. And so that comes out to be very simple vector algebra, minus 6750 newtons per coulomb I minus 4,900 newtons per coulomb J. Okay. Now, that is writing the answer in component form. Okay. And that's perfectly fine. You can leave the answer in component form unless I asked for the magnitude and direction. So what would be the magnitude and direction? Well, that means at this point, then it's got an electric field here. There's the X part, there's the Y part, and so the magnitude is right there. So we can find the direction here, theta, we can find the direction, and we can find the magnitude. Okay, Pythagorean theorem gives us the magnitude of it. So that's going to be the square root of EX squared plus EY squared. And so that'll be the square root of the 6750 Newton per coulomb squared plus the 4,900 Newton per coulomb squared. So the magnitude comes out to be 8340 newtons per coulomb. Okay, so theta is the inverse tangent of the EY over the EX, and so that's going to be the inverse tangent of the 4,900 newtons per coulomb divided by 6,750 newtons per coulomb. So that comes out to be basically 36 degrees. Okay. So I could say that the total electric field is minus 6750 newtons per coulomb I minus the 4,900 newtons per coulomb J. That's writing it in component form. Or I could say that it is 8340 newtons per coulomb at an angle of, well, what angle did we find? We found the angle there below the negative x-axis. So I could say the angle is 36 degrees below the negative x-axis. Okay, or the negative x-axis is often regarded as 180 degrees from the positive, so if it's 34 degrees more, I could have said that's going to be at an angle of 260 degrees with respect to the positive x-axis. Okay, that's how they normally do it in math. Now, either of those angular measurements is correct, and I would take either one of those. Okay, if you give an angle, try to tell me what you're measuring the angle relative to, and if you correctly give the angle with the measurement, you know, in other words, if you give the correct angle relative to what you're measuring to, I take that. So I would have taken, if I just said what's the electric field, I would have taken any of these three ways of putting it. Now, if I say what's the magnitude and direction, it has to be one of the two ways that are below. But I'm going to be a little bit generous here. If I just say what is the electric field, you may give it to me in component form, or you may give it to me in magnitude direction form. Either way. But if I say what's the component form, it needs to be component form. If I say what's the magnitude direction form, it needs to be magnitude and direction form.